Hi everyone, this is Freddy Meny working with Omar, Odeh, and this is our physics project on integration. Integration, it's a very useful skill to have in AP Physics C, and for those of you that aren't in multivariable calculus this year, this lesson will be very helpful to you. Basically, integration is the area under the curve. It is also the same as the opposite of a derivative, in such that similar to when you learn multiplication and division, how they are opposites, integration and taking derivatives also work in the same manner. So integration is the area under the curve from a certain point to another point, which can be expressed in this notation. The squiggle line is the notation for the integral of from a to b, which would be two values on an x-axis of a function f of x with respect to x. Or if it is an indefinite integral, then you do not include the a to b. And when you do an indefinite integral, after you take that integral of the function f of x, what you have left over, you have to have a plus c constant at the end of that. In this example, when you can see, if you took the area under the curve from 1 to 3 on the function 3x, you set up your notation as so, and then when you take the integral, it's the opposite of a derivative, in that instead of subtracting the power by 1 when you would take a derivative, you add and multiply that power by the coefficient. You add 1 to the power and divide by the new coefficient. So let's see, so we have 3x, so when we take the integral of that, we're going to get 3x squared over 2. So we add 1 and divide by 1. So you still take that from 3 to 1, and the way you find that on a definite integral, you plug in the numbers from the top and then subtract it from the function plugged in with the numbers from the bottom. So you have 3 times 3 squared over 2 minus 3 times 1 squared over 2. That will end up eventually giving you 27 over 2 minus 3 over 2, which is 24 over 2, which is 12 units squared. So the 12 units squared would be the value for the area under the curve of this function, also known as the integral. In physics, we can use these, especially when dealing with velocity, position, and acceleration. You learned that a velocity is the derivative, when you take the derivative of a position function, that will give you the velocity function. And when you take the derivative of a velocity function, that will give you the acceleration function. They work backwards in such that when you take the integral of an acceleration function, you will get the velocity function. And when you take the integral of a velocity function, you will receive the position function. Now we're going to do a little experiment here in the car, and we'll use that to interpret some more integrals. Alright, here we go. AP Physics C project. We got Omar, the driver. So what I'm going to do is I'm going to have this stopwatch. Once I click start, Omar's going to hit this from 0 to 50 right here, okay? So 3, 2, 1. Actually, keep going to 80. Alright, 0 to 60. We got 0 to 60, but yeah, it was still pretty nice. Alright, so by using that, we're going to find our acceleration, and we'll get right on back to you with the whiteboard.
Hey guys, so the last time you were with us, you saw us go 0 to 60 in 13.42 seconds in my car. I went ahead and did some conversions for you already. So 1 mile per hour is equal to 0.447 meters per second. So we get that 60 miles per hour is equal to 26.822 meters per second. From then on, we find the acceleration, and we can do this by subtracting our second velocity from our first velocity and dividing by the change in time. We do this, and we get 1.998 meters per second squared, and we're just going to round up to 2 meters per second squared because it is very close. So right here, I've let you know that if you're given a position function with respect to time, and you take the derivative of that with respect to time, that will give you your velocity function. And if you go ahead and take the derivative of that, it'll give you your acceleration. So with this knowledge, we know that if we took an antiderivative or an integral of acceleration, it'd be moving backwards, And the integral of acceleration would actually give us our velocity function, and our integral of our velocity function will give us our position function. So we know that the velocity at 1 second is 26.822 meters per second, and the position at 1 second will be 26.822 meters of the way in. So we go ahead and get started, and we take the integral of 2, which is our acceleration, with respect to time, and that gives us 2t plus c, and that is equal to our velocity function. So to figure out what our constant is, the c is, we can say that v at 1 second, which we know is equal to 26.822, we just go ahead and plug it in. So we get anywhere there's a t in your function, you're going to go ahead and plug in a 1. So it's 2 plus c equals 26.822, so c will give us 24.822. And to get our position function, we carry this down, and we take the integral of 2t plus 24.822 with respect to time, and we end up getting t squared plus 24.822t plus c for our position function. And to figure out this constant to give us our position function at any time, we go ahead and solve for the position at 1 second, which we know is equal to 26.822 meters. I'm going to go ahead and write the m afterwards. So anywhere there's a t in our function, we're going to go ahead and plug in a 1 again. So we have 1 plus 24.822 plus c equals 26.822. So we know that our c, or constant, and this position function is equal to 1. So our position function at any given time is t squared plus 24.822t plus 1. And you guys have a great day.